expert guest is Michael Lanagan. Why don't you just go ahead and introduce yourself to the listeners?
Sure. Yeah. Hey, everyone. Yeah, I'm Mike Lanagan, and my background is in materials, but I have a really strong interest in electromagnetics as well. So I started off as a ceramics science person that really studied high temperature properties of materials, and then really got interested in electromagnetics and how especially microwaves interact with materials. It's really useful for a lot of applications. But I know today we're going to talk about microwave ovens, but the microwaves are so interesting for radar and telecommunications and all those other things. It's just a great field to be in.
Yeah, so I wanted to talk about microwaves because I'm trained as an engineer and physicist, and there's still things that I don't quite understand about how they work. They're kind of unintuitive even for somebody like me. So I figured there's probably also not a lot of people who really understand how they work. And it's not just how they work, right? Because there's some basics of just how microwaves interact, but they also do some kind of weird things sometimes, like they spark, or you see YouTube videos where they create plasma. So there's all kind of these weird things that you can do with microwaves also that like are kind of unintuitive and need some explanation. So I thought it'd be fun to go into all of those things.
Right. Everyone almost has a microwave oven. So everyone really has the experience with microwave interactions with their food, at least. And so, yeah, I think it's a great subject.
Yeah, sure. So when I started thinking about this, some of the questions that came to me is like thinking about what actually is happening inside the microwave, what is actually heating up, because it heats up your food, but there's a bunch of other things in the microwave. There's a glass tray, you put a plastic cover over your food. None of that heats up. It's made of metal, and the metal walls of the microwave, none of that is heated up, just your food. So I figured we'd learn about how microwaves work and how that works. I want to look into why when you do put metal in the microwave, sometimes it makes these sparks. Maybe we could get into the screen in the front and how that actually keeps the microwaves out. What does it mean for the waves to not be able to fit through a hole? The way I think about this, microwaves are part of the electromagnetic spectrum. These electromagnetic waves have a particle and wave duality. Sometimes it makes sense to talk about them in waves. Sometimes it makes sense to talk about them in terms of particles. In this sense, I think it makes the most sense to talk about them as waves. So basically, in your microwave oven, you have an oscillating electric field and an oscillating magnetic field, and those kind of go together, right? It's wavelengths that are much longer than light, shorter than radio. And I guess to get started with how it absorbs things and how it works, the way I think about it is that just like light thing where there's materials that can absorb and some that reflect microwaves, right?
Yeah, definitely. So if you think about sort of the equivalent of a black surface when you're putting visible light on it, that would be a microwave absorber. And something that is equivalent to a window is equivalent in the visible range is equivalent to something that can transmit microwaves easily. So yeah, you can almost think about it like light waves in terms of light waves reflecting, absorbing, or passing through something. Since a microwave is also electromagnetic, just like a light wave, it does exactly the same sorts of things. Only the wavelengths, of course, are much longer, on the order of inches or centimeters, versus light, which is really, really small wavelengths.
So that sounds like a good place to start with, is look into kind of more specifics into the materials and the specific material properties that we want to learn about and how they interact with microwaves, right?
Yeah.
So there's basically three mechanisms that microwaves interact with materials, and they're kind of described microscopically. Like a lot of things we understand, we have these microscopic interactions, and these give rise to sort of macroscopic properties, right? The main ones, it seems, are electrical permittivity, which is the ability for a material to electrically polarize in an electric field. Magnetic permeability, which is the ability for a material to magnetically polarize in a magnetic field. And conductivity is the third one, which I think most people are probably familiar with. And that's just how an electric charge can move through a material. And that's due to an electric field.
Right. So if you think about all these properties, they're really at the atomic or electronic scale. You mentioned movement. That's exactly right. So permittivity is related to movement of charges, essentially going back and forth. If you apply some electric field, the charge will move in that field. And if the electric field is oscillating like a wave, if it's moving back and forth like a wave, then that charge also moves back and forth, and a lot of interesting things happen. I think we'll talk a little bit about charges at some point. Sometimes the charges are like electrons. Sometimes the charges are actually molecules. So maybe charges that are grouped together. So it's really fascinating to think about how charges are built up and move in an electric field. And then conductivity actually is very similar because their charges also move, but they're not really restricted. In conductivity, the charges move very long distances, whereas in like permittivity, the charges don't move so far, but in conductivity, they move quite a distance. So both those are associated with electric field, but then permeability also is movement, but in this case, it's movement in a magnetic field. And so now charges do some really weird things, like they do spinning. And so the forces of the magnetic field on a charge are very different for a magnetic field. But I think for the most part, for the microwave oven, we almost always think about the electric field. Even though electric and magnetic fields are in the microwave oven, we really focus on the electric field.
Okay. So it sounds like any of these properties really are decent candidates for investigation if we want to look into how the microwaves are being absorbed in the food and in the materials that we're interested in. So I guess you kind of dismissed the magnetic field a little bit. So let's just start with that, talk about I guess what magnetic permeability is and maybe why it doesn't matter so much in this case. Because yeah, we want to kind of not just say why it doesn't work, but try and understand and prove it, right?
Right.
Okay.
So
yeah, so my understanding of magnetic permeability just means that the ability for a material to magnetize in a magnetic field. So we normally encounter this with like ferromagnets and different types of iron, but most atoms and things do sort of react to a magnetic field, and they have they're in their subatomic particles, they have spins and they interact with that magnetic field in some way, right?
Yes, definitely. But most of the time, the strong interactions with magnetic field mainly occurs in metals like iron. And if you look at the periodic table, they're called transition metals, or rare earths are another set of materials, so normally metals that interact with magnetic fields. Typically, they interact very strongly with the magnetic field. But again, going back to the oven, a lot of times, people are putting in their food, and anything that normally is organic, like food, or even plastics and most glass or things like that you would see in a microwave oven, none of those things actually are very strong magnetically.
Okay, sure. Yeah, I tried to look up different materials, like tried to quantify basically the permeability of different materials, and they're basically all just one, which is basically just air, except for a few select metals, and those are the ones we think of as magnets, right?
Like yeah. Iron, that permeability of thousands.
Yeah,
right.
Yeah. Okay. So it seems like that's probably not a good place to look at if we're trying to figure out what microwaves are doing inside our oven. Okay. So let's go to the electrical permittivity, right? I know that's what you study a lot of, right? You study materials that are have a high electric permittivity. Yeah. So my understanding of electrical permittivity is that it's an insulator actually, but it's a material that can be polarized in an electric field. And what this means is that the charges don't actually flow through the material like they do in a conductor, but instead they just kind of shift from their equilibrium positions, right? So the positive charge shifts in one direction with the field, and the negative charge kind of shifts in the other. And this can happen by several different methods, depending on like the structure of the atom or the molecule, or whatever the material is can determine how these poles kind of orient or move in the material, right? So there's different ways. You can start with just the very basic atoms themselves can polarize in a field, right? We learned in chemistry that there's a nucleus with a positive charge and an electron cloud around it with a negative charge, and the cloud itself can kind of like shift in an electric field, right?
Yeah, definitely. So you're right. So that's one way. And what's really interesting, if you think about how materials operate in an electric field, first of all, they polarize, like you said. If they conduct, that dominates. So a lot of times when we think about permittivity, we think of non-conductors. So you really look at materials in two different classes, the way they respond to electric field. Either they're a metal and they conduct, and those metals all have they all have atoms that move as well in electric field, but everything's so shielded by the moving electrons that you really don't get to the point in the microwaves where you really see the ions moving. It's really all shielded by the moving electrons. So so once you get rid of that electronic conductivity, or actually ionic conductivity, then you could actually see the permittivity in the material.
I see. So it needs to be an insulator, even though metals may have this property, they just don't get to do it, basically.
Not at microwave frequencies. Anyway.
I see.
If you go to high enough frequency, maybe then you can see it. But at microwave frequency, if it's a conductor, you're not going to really be able to quantify the permittivity because conductivity dominates.
I see. Okay. Well, there's a few other ways that this happens. So you have dipoles, which is molecules like water that have, the based on the structure of the molecule and the bonds, you have a charge on one side of the atom versus another. And so this causes just the molecule itself to always be a polarly charged molecule, right? And then this orients itself in an electric field. And then this can also happen with ionic bonds. So things like salts, right? You have two charges that are bonded together with an ionic bond. And so these create two things, and they don't move like they do in a liquid or anything, but they're in a crystal and they can sort of shift their position relative to each other and relative to the other atoms in the crystal. And this creates, some sort of change in the electric field based on this movement.
Right. So the electric field interacts. You've described all these polarization mechanisms. First, you have the electrons moving back and forth. You think about the atom and the electrons orbiting the nucleus, and the electric field definitely moves them around. And electrons are fast and zippy and light, so they can respond to super high frequencies in actually the visible range. And then the second thing you mentioned were ionic crystals like salt. So you have sodium, which is positively charged within a salt crystal, and you have chlorine, which is negatively charged within a salt crystal, and they move opposite to each other in an applied electric field. And so they basically vibrate against each other. And these frequencies are typically in infrared, so still way above the frequencies for microwaves. So they definitely interact with a microwave. And then what really gets interesting, the third polarization mechanism is called dipolar, which is like you were talking about, where it's a molecule like in a liquid or a gas that basically rotates within the medium under an electric field, and they tend to rotate at the microwave frequency, which is really important, I think, as we'll get into that.
So the molecule itself is neutrally charged. It just has a pole, so it doesn't move in the field. It just rotates in the field. Is that right?
That's right. It just rotates. That's right.
Okay. So I looked up some materials to try and get an idea, things you put in the microwave to see which ones are best at react or best at, getting this dipole reaction going. And so you start with things like air is one, because it's really hard to polarize. That's kind of the standard, just base level.
Close to vacuum, right? Vacuum's one, and air is just a little above one. So you're not doing much better than nothing with air. Yeah.
So paper is a lot of air, and that's just over one. Plastic and glass have kind of a range, but they're like around like 5 to 10-ish, maybe even lower sometimes. Salt can be like up to 15. And what does this number mean? They just give a number, and it's a dimensionless number, right?
Right. Okay. So basically, if you have two parallel plates and you put a field on it and you put the material between those plates, you basically can charge put more charge on the plate. So those dipoles in the medium, like salt, if you put like a salt crystal in there where you have the two metal plates on both sides, you're making a sandwich. It's called a capacitor. And then you basically apply an electric field. You can store 15 times more charge on those metal plates than if you just had air or vacuum. So it's the ability to store charge and the ability for the material to respond to electric fields. So you can say that the salt crystal responds 15 times more than air in an electric field.
I see. So it's just a ratio then.
It's a ratio with
to a vacuum. I see. Okay. So there's a few more things then that you might put in the microwave that have higher numbers. So alcohol is like 30 to 40, water has about 80, but ice is very low. Ice is about 3. And I guess that's because the molecules then are kind of stuck there and they don't rotate.
That's right. They're clamped.
And then other things like olive oil and butter, different oils are quite low as well. They're like 2 to 5. Sugars, I don't know. I couldn't find it, but it seemed like every time I saw it, they needed to put water in for it to react. It seemed like every recipe, everything I saw with sugar, you needed water in the microwave or in the mixture with the sugar in order for it to heat up.
That's right. Yeah, sugar probably is on the order of 3. I'm guessing just by knowing a little bit about organics and so they won't interact with microwaves at all. So yeah, you can have dry sugar in your microwave and you'd have to work really hard to heat that up.
Okay.
Right.
And and then I think most carbohydrates are probably around there and protein as well. Okay.
Yeah. Almost everything that is like a plastic, which has a carbon chain, or sugars, or anything that's carbon based and solids, especially anything that's carbon based with some hydrogens and oxygens and they're organics. They're typically somewhere between 3 and 5. It doesn't change. Anything above 5 is really special for an organic with carbon, like a carbon based material. You mentioned alcohols and water. Alcohols, because they're liquid and they have these OH groups that are really polar, they can move quite dynamically in a microwave field. And of course, water is the best, it's probably one of the most polar materials around. It's like amazing material and has, of course, 2 hydrogens and the oxygen. The hydrogens are positively charged and the oxygens are negatively charged. And when you put them together, they form this plus minus dipole that can orient itself in a microwave field and rotate in a microwave field. And so has the strongest response out of probably almost out of any liquid. It's up there. There might be 1 or 2 liquids that have a stronger dipole, but water is probably one of the top. But alcohols are also pretty good. I mean, they have these OH groups that are natively charged, and those natively charged.
And water's a big part of all the food that we eat. It's what, right? Or we heat up just water in the microwave sometimes. So that seems like a pretty good candidate for what's doing the main absorbing of microwaves and converting to heat in our ovens, right? The one that confused me a lot though is because I melt butter and coconut oil and things like that in the microwave, and that seems to heat up just fine as well.
Yeah.
So I was, it absorbs it fine. I guess I don't know. It confused me when I came across that.
Yeah. So I mean, just think about like if you have a kilowatt oven, I mean that's a lot of power. And you think about if you tried to touch back, if you have an incandescent bulb that is actually a 100-watt bulb, you can't put your finger on that bulb. So a kilowatt is a lot of power. And then what we talk about that is there's 2 things when we talk about permittivity. One is the real part, which is basically what we've been talking about. It's like 10 to 15 for crystals, and it was like 3 to 5 for polymers. That number is related to the ability for the material to polarize. It says nothing about how much energy is lost. That's actually in the imaginary part of the permittivity, because these are all time-dependent properties. And what happens is when that imaginary part gets high, that's related to loss. That's related to the conversion of the electromagnetic wave energy to thermal energy. And so like butter may only have like a permittivity, say 5-ish, but it may have a loss that's pretty high in the microwave range, maybe 0.5 to 1. And so then what that does is the higher that number, the more of that power from that kilowatt source gets converted to the thermal energy in your butter. So it's just that you have a lot of power in a microwave oven, and you convert only a fraction of that into melting butter. But maybe you turn that into tens of watts or 5 to 10 watts, and that's probably enough to start the butter melting in a spot, right? And you can calculate how much it takes if you know heat capacity, and how much the enthalpy is. I mean, you can calculate how much energy went into that spot of butter. That's it's probably not that much in terms of joules.
Yeah.
You know how much time it takes for that wattage to get to that butter piece. So yeah, I mean, it does. So even though the permittivity is low, that's not the most important thing. It's the loss.
I see. But let's talk about what that means physically in the material, the loss, right? Because we talked about a bunch of these things with very low permittivities, and that's the ability for these materials to polarize. But then it seems like, okay, once they're polarized, it doesn't necessarily mean they convert all that energy back into heat. So it sounds like there's another property in the material that is the loss. And once they're polarized, then it converts the energy that they absorbed through that reaction into heat, whereas maybe some others don't.
Right. So that really gets down to when you have this response. For example, water has, we said, the oxygen was 2 minus, and then you had the hydrogens, which were positively charged, and then you can rotate this, and then the microwave is rotating the molecule at a million times per second. So that thing's really moving back and forth. And you almost think about your hands moving back and forth. You hold them together, you're moving back and forth. You can do that maybe, 10 times per second. You can move your hands back and forth, maybe 20, just rubbing your hands together. And, the faster you rub those hands together, the hotter your hands are going to get. And so basically that's what it is. It's basically moving something with some frictional forces. And that's sort of the conversion of the electromagnetic wave, which basically oscillates the molecule to thermal energy. Is you can think of your hands rubbing together and oscillating back and forth. Now let's look at something that's lower loss. That would be like rubbing your hand on a slippery surface. You just keep rubbing it back and forth, and it's not going to heat up. So that would be a low loss oscillator. So that would be the equivalent of a low loss material. So even though your hand moves a certain distance, and that distance moved can be related to the response, which is related to the permittivity, but moving it back and forth on that surface then is related to loss, because it is an oscillating system as well. So you have the response, how much it moves, related to the permittivity, the real part, but then the loss part is related to the motion and those frictional losses, I think is the way to explain it. So yeah. So even though it has a high permittivity materials, that's not the whole story. I mean, you want it to move far back and forth, because if you do have frictional forces, then you'll get a lot of heating. But you can have large frictional forces without having a large permittivity.
Yeah, you got to have that reaction to begin with, that polarization reaction, just to get it started.
Right.
So that sounds like it answers pretty well some of our first question about things. We do still have one more material property I guess we can go into, and that's conductivity, though. That's definitely something we also consider in microwaves. From my research, though, it said that microwaves are largely reflected from conducting material. I guess you kind of said that before, that they don't have this dipole effect, this dielectric effect, because the electrons are moving over the surface. For that's a highly conducting material. But I guess when it's less conductive and it does get absorbed, then the heat is transferred, just similar to what we were just saying, but through the resistive heating mechanism, right? And then insulators, I guess, act in the opposite way. They don't shield it. They don't reflect the waves. The waves just go right through it. Is that right?
That's right. So that means no loss from the permittivity, and no conductivity either. So basically it's the same as light. So if you have a reflective surface, normally it's like a silver mirror. It's a good conductor and it reflects the wave. So exactly what happens when you look in a mirror, exactly happens when a microwave hits that surface as well. It perfectly reflects it.
So how does that happen? Like what's sort of the micro interaction that's going on there?
Well, you do have electrons on the surface moving. So they'll basically move in a way that will basically create a boundary condition to reflect the wave back. And so basically the electrons are moving at a certain skin depth and maybe like a micron thick a layer of that metal will actually have electrons that move and respond to the microwave in a way that they create a boundary that
Okay.
basically reflects. Yeah.
So yeah, so what does that mean then for them to reflect a wave? How do we think about that?
Yeah. So they basically move they move with the microwave and then generate their own electromagnetic wave back, I guess, is one way to think about it.
I see. Okay. They're just moving along just with
Yeah, they're not losing, and they're hardly losing any energy. They're just like, moving along the surface and responding to the microwave.
I see. Okay. But then so what happens with like a semiconductor, something that's
Yeah.
partially conductive?
So those are the best absorbers because the microwave makes it in. It has a certain penetration that's pretty far, but it's also resistive. And those electrons basically are losing energy as they're moving. So it's not a very good conductor. And actually, those are the best microwave absorbers of all, are the semiconductors, because they will lose a lot of energy as it penetrates, and they can penetrate pretty far.
I see. Yeah, and so to look at some materials that are semiconductive, a lot of food is probably semiconductive, right? Like again, in our science classes, many of us have made like lemon or potato clocks, and the point of that is that they conduct through the body of these fruits or vegetables, right? And so there's some conductive material in these foods.
Right. So they have intermediate conductivity. Like when we say semiconductors, normally we mean like silicon, which is a electronic semiconductor, but foods are ionic semiconductors. They also have intermediate conductivities between metals and insulators. So yeah, foods are really prime semiconductors or ionic conductors. Yes.
Hmm. Okay. So it sounds like both the conductivity and permittivity play a role in absorbing energy and converting it to heat in specific materials. And what we're concerned about with is our food, mostly in the microwave oven. Do you have any intuition or knowledge of which one dominates here, which one produces more, or they kind of are similar?
I
I
think it
don't know.
depends on what you're cooking. So if you're doing a cup of tea, probably you're using the dipolar response of the water mostly to generate that heat. But if you put a lot of salt in there, salt water, maybe then you put enough salt in, then the conductivity starts to become important. So I think it depends, how much water you have versus how much salt or ionic content you have in your food and liquids.
I see. But that's probably the big one is the water, and then whatever's dissolved in the water in your food is kind of the main thing that's interacting with the microwaves.
Yep.
Okay. Okay, cool. I think we've more or less answered the first question then. So we can move on to we just talked about conductivity. I'm sure many of us have stuck a metal thing in the microwave and had it spark, right? So if conductors are just reflecting microwaves, then that's not what's happening a lot of times when they're creating sparks, if you leave a fork in there or something, right? So let's talk about electric arcing in a microwave, right? So electrical arcing happens when conductive materials are present. It doesn't happen always, of course. I watched a great YouTube from this guy, Electro Boom, and he was putting all different kinds of metals and spoons and forks and crossing them and connecting them and foil, and he was doing a lot of different things to try and get the metal to create an arc, but it was actually quite difficult.
Yeah, what surprises me, I know when we bought our microwave oven, they give you a rack that's metal that you can put right in the oven. It's like, wow, that's amazing. You put this rack in there, doesn't that spark? I mean, it is metal, it's got metal rungs on it, it's a shelf, and it's got a lot of metal. It's like,
A
why?
lot of surface area, a lot of
Yeah.
connecting pieces. Yeah.
but there's no thin, sharp places on that rack, I think,
Okay.
right?
Yeah. So the way I had it explained when I looked it up online is it said basically, like we were talking about with the electrons in a field, is that these electrons are just constantly getting sloshed around in the material, which is fine normally until maybe they get to a point, you have a sharp point in the material, and then they sort of all group together, and then you get a high concentration of electrons or just of charge, right? And then if there's enough of this charge, they can ionize a molecule from the air.
That's right. And then create the spark. Right. So it really is related to electrons moving along surfaces, but now they move to a surface and an edge that they crowd. And then once you have a crowd of charge, then you have a huge electric field that can ionize air, which sparks the air. So yeah, that's a very different sort of approach in terms of using metals. It's the geometry of the metal is critical, like a foil or something.
Mm-hmm. Yeah, and so this was quite different than I'm used to thinking about creating sparks or electrical arcs, right? Because normally when I see it happen is you're connecting two live wires, and they're like as they get close or even as they touch them, they create these sparks, right? Or if you're arc welding, you have a high voltage and a low voltage, and then you're creating some current between them, and that's creating the arc. But in this case, it seems like you just have a point charge, and then that's enough to ionize the air around it. How does that?
Well, I mean, it's pretty similar. So the breakdown of air is like 10,000 volts per centimeter or something like that. So if you know the electric field, the field could be quite local. So, if you have 10,000 volts and you're holding these two probes like a centimeter away, and then you say, oh, well, I'll put 10,000 volts on, you'll get a spark. And then, then if you go a millimeter away, then you only need 1,000 volts. So what happens is locally in a microwave oven, over a very short distance, you can have kind of a low voltage. It doesn't have to be thousands of volts, but basically it's many volts over a small distance. That's a huge electric field if the distance is small, and you can ionize and break things down. So it's still related to the breakdown of air, and it's related to the field, not to the voltage. It's related to the field, which is basically the voltage divided by the distance. So locally, over very small distances, you can get sparks. And that's what microwaves do.
And so is that related to like what we were talking about before, where there's some time delay in the way that these charges move? Because if you just have like a DC field, are they ever going to just spark with the air, or it needs to be sort of some delay where these charges are moving and then the field that got them there has moved on or something, and so you have a lower field nearby? Is that what's doing it? Or
so are you saying because a microwave you put in the oven, it may take a little bit for the spark to start? Is that what you're saying?
Well, or that they don't necessarily follow perfectly the electric field, like in any given time there's some delay. Is that a good way of thinking about it? Because the charges will align themselves in an electric field and
Quickly.
yeah, but I mean they're not going, but the field is this more or less the same all around them because that's how they got there, or no?
Yeah, the electric field, I mean, in a microwave oven, we're talking about that. You have these stirrers. And so the reason why maybe you don't get sparks like immediately, or you might, but it may take a second or two because the fields are changing within that microwave oven. And you just catch the wave, so to speak, where the wave pushes the electrons to an edge. That just kind of may take a little time for the microwaves to align themselves because there's a lot going on with the microwave oven. Delay, there's not really I mean, these things are moving really fast. So the electrons are moving to the edge very quickly and generating a spark. But sometimes you don't see it so fast in a microwave oven. I think because they have these microwave stirrers and the electric fields are changing over seconds, probably. So I don't know if that's what you mean by delay or not.
I guess I'm trying to think what creates that gradient. Is it just that the wave itself is an electric field gradient?
Yep.
I see.
That's
Okay.
right.
Because you hold up a wire and it can be, whatever voltage. If there's no low voltage thing for it to go to around, it's not going to start sparking, right?
And it could if it was high enough voltage, and then then it's looking for a ground somewhere, right?
I see. Okay.
but it's far away. I mean, basically whatever wherever it's trying to find is maybe a meter away, which is huge, right? So that'd be huge voltage.
Okay, so let's talk a little bit more about the waves in conducting material then, and like kind of the size and what it means for them to be moving these electrons around within the material. I suppose you'll create different reactions based on the size of the wave, right? Or like, and the geometry of the conductor that you have in there, because you have to draw the charge from the bulk material, I suppose, right?
It's running it so you have charge at the surface. I mean, basically electrons are all over the metal. They're pretty homogeneously distributed within a metal just sitting there. But then once you apply your microwave to the surface, only electrons at the surface move within the micron, and they'll move quite quickly. And they'll move back and forth along that surface till they get to an edge. And once they get to an edge, they stop. And when they stop, they're piled up. And when they're piled up, then they can generate that spark.
Okay. And they're piled up from the size of the wave, bringing all of them from that field for the size of the wave.
Right. Because the wave, you can think of the wave basically is running along the surface at that point.
So I guess my thought here is just you could shine. This doesn't happen with light, right? If you shine a really bright light on the metal, that doesn't.
You're not moving the electrons as the same way.
Right. Okay.
Basically, you're not, when you shine light on a metal, you're not interacting with a micron of surface. You're interacting with a much smaller depth, for one. So you have less electrons probably to move. And second of all, the microwaves, since they're centimeters long, you're driving these things probably at longer distances along the surface, right? So you're probably crowding more electrons on the surface.
Right. Okay. Yeah. So let's talk about that a little bit more. Let's talk about how the microwaves are actually in the oven, like what's actually going on with the waves themselves, the size of the waves, and how they're being generated and how they're being reflected off the walls, I guess, because they're not being absorbed in the walls. So let's talk about that a little bit. From my research, just said that the microwave ovens have metal walls that are needed to contain the electric fields, right? So that, as we were saying, they basically bounce the electric fields off of them. And then what happens is this results in a three-dimensional sort of pattern of high and low electric fields, creating hotspots and things in the microwave.
Yeah. So, I think we were talking about this earlier, where even, and a good analogy is like sound waves in a room where you have echoes sometimes, especially in a room that doesn't have drapes in it and doesn't have carpeting, or, I mean, if you're in a hot room, so to speak, acoustically, you're going to get all kinds of echoes. And then in those types of rooms, if you stand in certain places, you're going to get no sound at all. And so, some people in theaters, they worry about this, obviously, because they want to have all the patrons listen to the sound in the same way. So they really work hard to not have dead spots in these rooms. The same thing happens in a microwave oven. Instead of sound waves bouncing all around, you have microwaves bouncing all around, and you'll get constructive and destructive interference at certain spots. And some spots will be hot, and some spots will be cooler, because you have less microwave energy in those spots. Just because things are bouncing around. What the microwave companies, and I think you're going to get to this, and what they do for microwave ovens is they have rotating things, right? And we've all seen the rotating trays, and then they'll have mixers as well. So these are reflecting surfaces that they put, basically have vanes on the top of the microwave oven that move, and they stir. They call them stirrers. They stir the microwaves around. They steer or stir.
Yeah, I guess so that answers why you have the spinning plate in the microwave, because that's not an obvious thing. My initial impression of that was like you're shining it on one side, and then maybe you need to spin it to get different sides, but I guess that's probably not right.
Yeah, it might be a little of that. I guess I don't know enough about microwave design for ovens, but they do have a port on the side that the microwaves go in. I'm guessing that probably influences the microwave pattern. It's probably not that uniform in the oven, so that would be another reason to have these stirrers and rotating platforms.
So it seems like you could go a lot deeper into, you talked about acoustic waves, and it seems like you could go a lot deeper into wave interactions with themselves, with destructive and constructive interference and all that stuff. But I don't think I want to go there with this one, with this podcast. So we're going to stick to the microwaves. But similarly, I want to look into the holes in the screen, right? So we talked about waves. The microwaves act as a wave, and they're bouncing around the cage. And then they must also bounce against the front, against that metal screen that we see there, right? They don't go through those holes. So it's kind of curious, what does that mean for a wave to not be able to fit through a hole, right?
Right. Yeah. I have heard of people taking those screens out so they can look in there better. That's a really bad idea. It's amazing because you say, oh, I can see through it. So, it's not doing much, but you have to realize that it's blocking waves that are much longer than your visible. The visible wavelengths are on the order of 400 nanometers, right? So submicron wavelengths. And the screen, you look at the grid, and those holes in the screen are definitely bigger than that wavelength. So the waves can scoot right past those holes, at least in terms of the visible spectra. But because your microwave is like 3 centimeters or like 1.5 inches, on the order of 1 inch in wavelength, they cannot make it through that screen at all. And so it's basically just how big is the wave. The microwaves, it sounds weird when you say micro, you think they're small, but they're not that small. They're on the order of centimeters or inches. So if you have a screen that has holes that are, a fraction, or a millimeter size, they're definitely not going to make it through.
Yeah. So you talked about it as a wavelength, but to my reasoning, we're concerned if the wave's going, oscillating, does the height or the amplitude, is that what matters? Like, why does the length of the wave matter for getting it through something? Does that make sense?
Yeah, I mean, you can't think of it spatially in that way. I don't think, because these are sort of plane sort of waves that are moving through, and they'll interact with the metal screen in a way that, basically the wave will be distributed along that metal screen. And so if you can have something that's on the order of a centimeter to 1 inch, it's going to distribute itself along that screen and not be able to pass through. But I guess a visible wave, since it's on the order of 400 to 500 nanometers, it can distribute itself and it doesn't hit any of those wires at all. And so it can make it through no problem, because it can distribute itself in free space or in air without hitting really the metal. So maybe that's one way to think about it.
Yeah. Okay. So I'm trying to think of it this way. Like, so in order for it to go through a hole, it has to be going, perpendicular to it, right? Like the wave has to be traveling towards the screen, right? So that's what we mean by going through. It's going to be traveling that way. But the wave is traveling that way. But electromagnetic waves, the electric and magnetic fields are perpendicular to that, right?
But it's a front, right? It's a front.
Okay.
It's not like a single sinusoid like thing coming. It's actually like a wave front that's moving and oscillating as it propagates, right?
I see.
So yeah, you can't think of it as like a single sinusoid at all. It's basically a surface or a front of waves that has a potential that changes with time, essentially.
Okay. But a light wave also has that front, but it just doesn't interact then?
Right, because the wavelength's so small that it really doesn't have to interact with the metal.
I think that answers most of my questions, kind of early thoughts about how I was trying to think of the microwave and what's weird about it. Definitely, I wanted to talk about plasma, because that's something you always see with the YouTube videos, is like people doing all kinds of cool stuff, creating plasma in the microwave. And we talked a little bit about it, right? We talked about the spark generated by a conductor that starts to ionize the air, and that creates a plasma, right? But there's lots of other ways and ways to sustain them, and there's lots of cool videos you can see on YouTube of people putting all kinds of different things in the microwave, and they generate plasmas, right?
Yeah, definitely one of the more dangerous things you do, and with a microwave oven, but pretty exciting if you want to play around with microwaves. That's not recommended to do at home. If you have a microwave you don't mind destroying, it's kind of fun.
So the one video I was just watching was that they did what we were just talking about. They had a conductor, they used foil in a microwave, and they just put a beaker on top of it. And then that was enough to like generate the spark first, but then it was also sort of able to sustain this plasma in the beaker.
Yeah, once you get it started, so a plasma is like the fourth state of matter, that you can think of. Basically, they're clouds with ions. The electrons have now left the atoms in the gas, and the electrons, since they don't have a home, they're basically moving around that volume, and they're free to move around. They're not really contained next to a nucleus anymore. So they're free to go. And then they're really absorbing. A microwave hitting the plasma basically will be absorbed very easily. And the more energy you have, the more volume you can maintain with the plasma. So it takes a lot of energy to maintain a plasma, because if you stop putting energy into the plasma, the electrons will find their homes. They'll go back to each of the gas atoms, and you won't have your plasma anymore. So you have to really keep maintaining it. So once you start a plasma, it could start at a very small volume, and that could be generated by a spark. But to grow it, you need to keep putting energy in, and microwave is a great way to put energy into a plasma.
Mm-hmm. So when you see this sort of sustained kind of glowing plasma in the microwave, that energy is coming from the microwaves. It's not coming from anything like that you're burning, or like whatever you use to start the plasma. You're not consuming that. You're just putting energy in from the microwaves themselves, and they're being absorbed by what we just talked about, because this plasma is highly ionizing, so it reacts very well with the microwaves.
Right. It's a semiconductor, basically, I guess, is the way to think about it. You're dumping a lot of energy through that conversion of the electromagnetic to motion of the electrons and ions, right? So that's why microwaves are pretty efficient. And then you get to a point where you're dumping as much energy as you can, and then it's the plasma is losing energy, right? If you see light coming from the plasma, it's losing energy, it's losing thermal energy. So yeah, you get to some sort of steady state where you're dumping enough energy in through the microwave to maintain the plasma.
I want to talk about a few kind of specific examples of this to try and get your take on it, see if you can explain them for me. One of the popular ones, Veritasium did it a while ago, was you stick 2 grapes in the microwave. The explanation I saw was that it's based on the geometry of the grapes, or they did tests with hydrogels, I guess, which did something similar. And the way they said it was that because of the geometry, basically the microwaves are just able to be contained within those grapes or hydrogels, and then eventually you just keep pumping it up, and eventually they just get a lot of energy inside them until they start ionizing and ripping things apart to create the plasma.
Right. So electromagnetically, grapes are like the perfect musical instrument almost, because they're at the same size as the microwave. Now, if you try to put an apple in there, the apple's much larger than the microwave, and it won't resonate. And grapes are pretty neat because they'll actually resonate like a musical instrument. When you play the right note for your tuba, you put energy into the mouthpiece, and you get this resonance going, and you get out the bell, you get the musical note. It's a low frequency. As you go to say a flute or something, it's a much higher frequency. So here you're matching the grape, which is the perfect microwave frequency fruit, versus an apple, which would be like a tuba, too low in frequency, and maybe something that's smaller, like a raspberry, would be too high a frequency. Grapes are perfect. They are spherical, and they're right in the range of the frequency and wavelength of the microwave. So they work really well. Hydrogels, I'm guessing he made those hydrogels pretty much the same size as the grape, right?
Yeah, I think so.
Yeah.
Right. So is it like you see? So I guess if it's resonating at the right frequency, it means you can keep putting energy in, and it just keeps getting like,
Yeah.
you think of like those bridges that they design wrong and they like shake themselves apart basically, right? Because
Right.
the
Right.
wind goes and it resonates it, and you just keep putting energy in, and it just keeps getting, the bridges keep swinging further and further until eventually it just collapses on itself.
Yeah. The right frequency. Right.
I
So it's
see.
perfect. Yeah. So that's the reason why grapes work so well.
Okay. So help me try and conceptualize that a little bit more with the what that means in a microwave. So the microwave itself is resonating inside the grape because of conductivity that we talked about, or is it
The
the
boundary
dielectric?
conditions. So anytime you have a dielectric interface, so between the inside and the outside of the grape, you bounce waves back and forth within the grape. And so you get to a standing wave within the grape
Mhm.
because the boundary between the grape surface and air reflects the microwave back into the grape.
Okay.
And so you can set up a standing wave within the grape because it's the right wavelength.
Okay. And then what does it mean to have a stronger wave in there? Like if you keep putting energy into it, what does
Yeah. So you'll eventually get to a point where you'll get to a steady state as well. But that steady state is pretty strong in terms of microwave energy
Mhm.
going in.
I
So,
see. And then how
yeah.
does that ionize things to create a plasma?
So
What's
now
the
all of a sudden you have this steady state energy storage in the grape, and the electric fields are so high now that
I see.
they can ionize.
I see. Okay. And then another good example that I've seen on many videos is they put either matches or candles inside the microwave, and those generate plasma as well.
Yeah, because candles are a plasma to start with.
I see. And then you just keep dumping more energy in, and it creates its own sort of sustaining thing.
Yeah,
Always underneath the beaker, right? Because otherwise it just goes a little crazy, I think.
yeah, right. You got to contain it so it doesn't burn and go crazy. But yeah, Michael Faraday, I think, studied candle plasmas a long time ago. So yeah, I mean, that's really your starting plasma, whether it's a spark or a candle, which is a good way to have a plasma start.
And in those cases, the plasma itself is just from the air molecules. Then it's
Yeah, I mean, it's a high temperature source. You can ionize gas by temperature,
mhm.
and that's what a flame does.
Okay, because I watched this video where he was using a spectrometer and looking at the chemical compositions of different plasmas that he was generating in the
Yep.
microwave, trying to figure out what it was. And I think he arrived at basically they all just eventually degenerate into whatever's in the air.
Yeah, that's actually how they look at chemical composition. They have things called inductively coupled plasmas, which, they'll ionize your sample and they'll tell you what's in it.
All right, I think that answers like all the questions that I thought of when I was originally trying to think of how microwave ovens work and why I don't understand about them, right? We talked about what the microwaves are and how they interact with different materials, why they heat up some things and not other things, the specific material properties that do that. We looked at the metals in there and why they spark and why you should try and avoid putting conductive things in there, and then different things with the waves and how they move inside the microwave and interact with holes and metals and the geometry. So I think I understand it better now. Hopefully everyone listening does too now. And then we talked about some plasmas. So that's most of the things I've seen people do with microwaves. I thought we'd take this last section and you can just talk about your work, and hopefully we can understand some of it now that we have a pretty good understanding of microwaves. And I know your work is related. You do a lot of things with microwaves and materials. So if you want to promote your work, talk about it, try and educate some of our listeners about, the cutting edge or, some of the research being done in this field.
All right. Well, one kind of a related topic, we are working with a group to look at space propulsion. So one of the biggest problems with the rockets is that you have to have a lot of propellant on board to get the rocket into space, and then you basically have less room for payload. And we're working with a group at the Air Force where they're taking a directed energy beam. It's a little bit higher frequency than the microwave, but the beam is really high power, and they want to take the beam and point it at the rocket nozzle to heat the rocket nozzle up instead of having a propellant. So basically your energy source is on Earth, and then you keep beaming the energy to the rocket nozzle. Now we're trying to develop materials that absorb these these microwaves. They're actually called millimeter waves. They're a little higher frequency, but same principle. And so we're designing materials to collect the energy at the rocket nozzle and heat up the rocket nozzle to thousands of centigrade. So then it provides propulsion. So, it's the same principle, but it gives a really novel way to think about the propulsion.
And that would be to get it through the atmosphere, or once it's left the atmosphere? Because
that part I don't know.
Okay.
Honestly, I don't know that part so well, but all I'm working on is the materials that absorb the, it's actually 100 gigahertz, so it's a much higher frequency beam that they're using.
So I've heard about this from, they were trying to do this from before, like creating like solar sails, right? That's kind of a common idea for, and then you would shine a laser at it from like a spaceship or like from the moon or something, and then you could send a ship. But but you can create microwave lasers, is that right?
Yeah, sure. Yeah.
Okay, and that's probably what you would use to. Okay.
High power sources. Yeah. There's some really large facilities that they have. So that's one. I mean, obviously microwaves are used a lot in telecommunications, which is really neat, and magnetic resonance imaging, which is a little lower frequency than a microwave oven, but still the same sorts of concepts applied there as well. So yeah, lots of really cool, interesting applications. I think it's a really fun area to work in. So yeah, thanks for having me on the first podcast.
Yeah, great. Thanks for being here. We all learned a lot, I think. I certainly did.
Looking forward to future podcasts.
All right. Thanks a lot. We'll talk to you later.